is Kirchhoff. He's German, and he is responsible for arguably the most important law in circuit analysis, his voltage law. To first understand his voltage law, though, we need to understand this little guy. He's an electron, but we're going to call him Harry. Harry carries a charge of about 1.6 by 10 to the negative 19 coulombs, meaning you need 6.25 billion of him to make up 1 coulomb of charge. However, Harry can't flow around a circuit on his own. He requires a push. This is where voltage comes in. Voltage is like Harry's mum, Deborah. Pushes Harry around the circuit and makes sure he's actually doing something. A circuit ideally has zero resistance in the wires and the electrons are able to move freely. This is like pushing a crate across an ice lake. It is free, it is effortless. This is like a wire. A crate being pushed across a gravel road, however, takes a lot more work and energy. This is similar to the resistor. After pushing across the ice, you are still very energized and ready to go, as you haven't used any energy to move the box. However, going across the gravel road, you would be exhausted when you finished. To understand Kirchhoff's voltage law, we need to look at polarities of a circuit as well. It doesn't matter if it is a resistor, a voltage supply, a capacitor, or a inductor. If the arrow of the current is running from negative to positive, it is a negative element. However, if we flip that arrow and it is running from positive to negative, the element is a positive voltage. If we look at a quick example, a simple circuit with a current flowing through, Kirchhoff's voltage law states that the sum of all elements is equal to 0. Meaning if you plug some numbers in with a 10 volt input, a 5 volt dissipation across R1 and a 2 volt dissipation over R2 and an unknown across R3, we can use his equation here to do some very simple algebraic rearrangement to find that V3 is equal to negative 3, and plugging those back in, we have a complete circuit. Looking at a parallel circuit is slightly different. If we plug our numbers in, we've got a 10 volt input, a 6 volt dissipation across R1, but unknown on R2 and R3. We need to look at this system in two different sections, this one and this one. We first look at this one, doing some very simple calculations again. V2 is equal to 4 volts, and we do the same over here, and we find that V3 is also equal to 4 volts.